Okay, can you hear my voice?
Yep.
Okay, thanks. Hi everyone, I'm Jinkayo from MediaTek Research. And today I'm going to present the topic Polyak-type step size for mirror descent methods. This is a joint work with my advisor at National Taiwan University, Professor Yanhuan Li. And part of this work was accepted in ISIT this year, which is an information theory conference. But in this talk, I will mainly focus on the optimization theory part.
Sorry, excuse me. I hear quite a lot of echoes. I'm not sure what is the problem.
Okay, so do you hear echo?
I think currently it might be better than previous. Okay.
Okay, thanks. So let's recapitulate the abstract that I will talk about today. First, we will introduce the standard Polyak step size, and we'll give its convergence rates in the smooth end and smooth, strongly convex setting. And second, we will propose two variants of Polyak step size for mirror descent, and we'll prove their convergences for minimizing convex locally Lipschitz functions. And let's start with our outline today. So based on the abstract, first, I will give an introduction and the motivation of why we consider the Polyak step size and its variant. And then I will talk about the problem formulation and the prior knowledge, such as mirror descent and the standard Polyak step size, and its convergence rate guarantee. Then we propose two variants of Polyak step size and provide their convergence results. And finally, I will give a conclusion. And for the convergence analysis in this talk, I will not present the proof details line by line. Instead, I will focus on the technical issue and the high-level ideas of proofs that I want to convey. So why do we introduce the standard Polyak step size and give its convergence rates? Because modern machine learning models, such as over-parametrized models, can fit a training data set completely. Over-parametrized means that the number of the neurons is much larger than the number of data samples. And this makes that the optimal value of the objective function is usually known. Hence, the standard Polyak step size is an appropriate choice of the step size selection in the over-parametrized setting. But why do we need to propose two variants of Polyak step size for mirror descent in convex locally Lipschitz functions? This is because the standard Polyak step size requires the optimal value, which limits its applications in practice. And several applications violate the Lipschitz and smoothness assumptions, such as portfolio selection, Poisson inverse problems, and so on and so forth. And I will not go through the formulas of these problems. The audience can read these two papers for further details. And I will take a very simple function as an example to explain why Lipschitz and smoothness conditions do not hold in these applications. The minus log function in one-dimensional space, we can easily check that minus log function is convex and its gradient and Hessian are -1/x and 1/s squared respectively. When the point x is approaching 0, the absolute values of gradient and Hessian will go to infinity. However, standard analysis of convex optimization methods require the Lipschitz and smoothness assumptions. Hence, existing convex optimization methods and their convergence guarantee do not directly apply. And furthermore, the reason why we consider mirror descent instead of projective gradients descent is that projective gradient descent can stop. The word stop means that even we use the projective gradient descent, arguably the simplest convex optimization algorithm, the algorithm might not be well defined. This is because projection onto the set, for example, the probability simplex, it might cause a sparse vector, which means that a low rank density matrix in matrix case. And this causes the corresponding derivative might not exist. Then because the next iterate is not well defined, it can happen that projective gradient descent is forced to stop at a sparse iterate far away from the minimizer. And this phenomenon is called the stalling issue for the projective gradient descent. Okay, let's go to our problem formulations. We consider the following general convex optimization problem, where the set capital Z is non-convex closed convex set, and f objective function is convex. And we assume that there exists a minimizer, and the minimum value is finite. And if the set capital C is Euclidean space, then it is the unconstrained convex optimization problem. And if the capital C is the subset of the Euclidean space, then it is a constraint. And now let me briefly introduce the mirror descent first. Mirror descent can be expressed in equation 1, where dH is the Bregman divergence induced by some convex differentiable function h. When h is chosen as the square Euclidean norm, it is called the projective gradient descent. And when h is chosen as the negative Shannon entropy, it is called the exponentiality gradient descent. And the iteration rule of exponentiality gradient descent has a closed form. The capital C here is a positive number chosen for the normalization of the iterate. And we just talked about the stalling issue in the introduction section. This issue can be vanished when using an exponentiality gradient descent. This is because exponentiality gradient descent always generates vectors that each element is positive. Therefore, the corresponding iterates are always well defined. Roughly speaking, mirror descent is a first order method which contains the gradient descent and the exponentiality gradient descent. And it requires a quantity called the step size eta t here. The step size we introduced here is called the Polyak step size. And as I talked before, the original Polyak step size requires the minimum value of the objective function. One of the derivations for positive size is as follows. If we consider the distance between the iterates and the minimizer, by the definition of gradient descent, we can easily get the upper bound expressed by this inequality. And the positive size is that we minimize an upper bound on the distance of the iterate to the optimal value. And I will talk about some property of the positive size. When the objective function is L smooth and mu strongly convex, the positive size is bounded as follows. And we can, the lower bound of the positive size is expressed by a smooth parameter, and the upper bound is expressed by the parameter of strongly convex. And we can easily get this relation from these two lemmas. To be more specific, if we consider the unconstrained set, if we consider the unconstrained setting, and we plug the minimizer into X, and we plug the iterates ZT into Y, the gradient at the minimizer disappear because it is 0. So these two terms disappears. And after arranging the inequality, we can get the lower bound. And similarly, the upper bound can be easily get. And this is also the key property to prove the convergence. If the function is smooth, then gradient descent with the standard positive size converges as the sublinear rate, big O 1/t. And if the function is smooth and strongly convex, then gradient descent with the positive size converges at a linear rate. And I will not go through this proof. The audience can find these two papers for details. The first paper of Ile Hassan and Shem Kakade considers the deterministic setting, and the paper of Nicolas Louisou considers the empirical risk minimization setting.
I have a question.
Yes.
So these convergence rates that you just showed are the same as when using a constant learning rate, right? As opposed to, well, which is between some, which is bounded by, yeah, the same, basically the same bounds as this one. I mean, the Polyak step size is very specific because it changes in time according to the loss function and the gradient. But even if you use just a constant step size which satisfies this bound, then you have the same convergence rate, right?
Yes.
Okay.
But typically in many applications, we don't know the smooth parameter and the strongly convex parameter. So we cannot accurately choose the constant step size that range in that falls into this range. So so that's why the positive size, it is an adaptive step size that can adapt to the function and the geometry of the function.
Yeah, but you also don't know f of z star. So
yes, yes.
So you still cannot really know the Polyak step size. Okay.
Yes. But in the over-parametrized models, the minimum value is always known. So that's why these two papers propose the Polyak step size. Okay.
Yeah, thank you.
So let me continue. But as I talked before, the original positive side requires the minimum value, which is impractical for many applications. So we propose two variants of the positive size for mirror descent. The first algorithm is stated as follows. We replace the two norm in the standard positive size with the general norm here. And the minimum value is replaced by the estimated optimum. We want to reach the estimated optimum delta ft that is smaller by some scalar delta t over the best value achieved so far. Whenever the estimated optimum is achieved, we increase delta t or we keep it at the same value depending on the choice of the parameter gamma. If the estimated optima is not attained at the given iteration, delta t is reduced up to a prescribed threshold delta. And the second type positive size is another approach to evaluate the estimated optimum. In step 1, FT-rec keeps the record of the smallest function value attained by the iterates generated so far. And if the current function value drops enough, then we set FT record as the current function value. If the function value does not drop enough, the algorithm will recur the sum of the magnitudes of the gradients scaled by C eta t. If the magnitude exists some threshold B, the algorithm will decrease the value delta, which makes the step size smaller. So we can know that the estimated optimum updates only if step 2 and the step 3 is detected. Because in step 2, we will update FT record here. And in step 3, we will update delta. So, okay, let's go to our theorems. So in the theorems, we prove that if some regularity assumptions hold and the objective function is locally Lipschitz, which means that the gradient is locally bounded on any compact subset. The first type positive size is guaranteed to yield a delta optimal convergence result with delta positive and can be arbitrarily small. And second type positive size is guaranteed to converge to the two optimum asymptotically. So why does positive size work under the locally Lipschitz setting? Why do we initially think that the convergence can be proved? And I will give a high-level perspective here instead of showing the proof line by line. Let's recall that the minus log function we mentioned before, the gradient and Hessian are unbounded when the point x approaches 0. So in a high-dimensional space, it means that the gradient and the Hessian will blow up when the point approaches the boundary of the set which we consider. Hence, to avoid the unbounded gradient situation, we need to ensure that the iterates generated by the algorithm do not touch the boundary. And the Polyak step size obtains this good property. And let me use gradient descent as an example because it is easy to interpret by drawing a picture. Let's start with an inequality by a well-known result called the Bregman proximal inequality in the optimization field. When we plug the definition of the standard Polyak step size into the inequality, we can get the following relation. And it tells us that the distance between the next iterate and the minimizer is smaller than the distance between the current iterate and the minimizer, minus a positive value, because this term is greater than 0. So what does this inequality mean? It means that the distance to the minimizer is monotonically decreasing when we use the Polyak step size. Let me draw a picture to explain it. If we consider a general convex set, which is represented by a blue triangle here, the initial point and the minimizer are represented by Z1 and Z star respectively. When we run a gradient descent with the Polyak step size, the iterates will get closer and closer to the minimizer by the property that the distance to the minimizer is decreasing. So we can find a subset to contain all iterates. Therefore, we don't need to consider the entire space, which let us avoid the issue that the gradient might blow up at the boundary. And this is a high-level idea I want to convey. But there are actually some gaps between the idea and the convergence proof. And the audience can find one proof of the first type Polyak step size in this paper. So let me give a conclusion. We introduced the standard Polyak step size and gave its convergence rates in the smooth and smooth-strongly convex setting. And we propose two variants of Polyak step size for mirror descent and prove their convergences for minimizing convex locally Lipschitz functions. And there are some core ideas that I think it is worthy to take away. The first is that the stalling issue can vanish when using mirror descent. For example, the exponentiality gradient descent. And the abounding gradient issue can be avoided by the Polyak step size. Okay, and that's all from me today. I will stop here. Thanks for your listening. Any questions or comments?
Yeah, I have a question. Yes. So is it true that the assumption of smoothness implies that the Polyak step size converges to 0 near the minimum?
Yes.
Okay. So this resembles basically decaying learning rate that people use to train a lot of models. Also neural networks, where the learning rate is decayed. And it also reminds me of some necessary condition for convergence of stochastic gradient descent. So usually to prove that stochastic gradient descent converge, you need to assume that the learning rate also decays to 0. So, yes. So I wonder if there is any use of the Polyak step size in stochastic setting?
Oh, yes. For example, this paper discusses the stochastic Polyak step size. they run the experiment in the over-parametrized model setting. But because I want to simplify the content of this talk, so I just talk about the deterministic setting. And the convergence proof, I think the convergence proof in the stochastic setting is similar as the deterministic setting. They also use this property because the Polar stem size is bounded by the smooth parameter and the strongly convex parameter.
Thank you.
Yes. So does anyone have any questions?
Hello. I'm just wondering, can you emphasize the difference you made compared to the traditional method? Just show me the slide that that is the main difference of your work compared to others.
So you mean the theoretical results?
Okay. So this is the main contribution you made. Is that?
Yes.
Okay. Because so here you highlight that in your assumption f is locally Lipschitz. Does that imply that the main contribution of your work is to relax that assumption, or what? I mean, what is the difference between your theorem and the previous works?
Okay. In our theories, we relax the objective function to locally Lipschitz, and our Polar step size do not require the true optimum value. And in the previous work, most of them analyze the standard Polar step size for gradient descent and mirror descent. And under the standard assumption, which is that the objective function is smooth and strongly convex.
Okay, so my understanding is that the main difference you made compared to previous work is that first you do not assume the knowledge on the global optimum, yes. And the other is that you relax the assumption to be locally Lipschitz. Am I understanding correctly?
Yes, that's true.
Okay. Okay, and I'm just wondering, so now your contribution is that even without the knowledge of the global optimum, you can still compute your algorithm, right? And what is the difference between knowing and not knowing the global optimum? I mean, if you know global optimum, maybe you can converge more quickly to the global optimum, right? But if you do not know the global optimum, maybe you converge slower. So I mean, what is the price you pay by by approximating the by guessing the global optimum with your algorithm?
Because we use our algorithm in the information theorem field. And let me skip to that slide. So we consider these 4 optimization problems that we cannot know the true optimal value in advance. So that's why we use the process that estimates the optimal value.
Yeah, I understand that you can solve some problem which previous work cannot do because you do not need you do not require the knowledge of the global optimum. I totally respect that. What I'm asking is that in problems where traditional methods can do, namely you know the global optimum, and I'm wondering if now you deliberately hide that global optimum and use your algorithm to guess that global optimum and do your algorithm. What is the price you make? What is the price you take? I'm asking this question because I'm just curious, like how good your approximation to the global optimum is.
How good? Because the approach for estimating the global optimum, because we if we think approach that can estimate the global optimum, we cannot get its convergence proof.
Okay, so if I understand correctly, what you meant is that you have an algorithm which can guarantee eventually it will converge to a global optimum or global optimum plus some very small amount delta, yes. But you cannot prove the convergence rate.
Yes,
yes, you made.
We already proved asymptotic convergence.
Okay. And I'm wondering if you have any idea if you want to eventually prove the convergence rate.
Yes, we think about this research direction, but unfortunately, we currently cannot get a convergence rate now. So it is our future work.
Okay, I'm wondering. I guess you must have like spent a lot of effort in like constructing proofs, trying to prove the convergence rate. And towards the end, I guess you may have also like think of like weird cases or the worst case scenario you can think of that has the slowest convergence rate under your algorithm, right? So I mean, what kind of setting in your imagination might be the very worst very worst case scenario in your where your application applies? I mean, if you want to, if I were you, I want to prove a bound, right? I will try my best to construct some examples which will work very badly. So in that case, I can think of well how to deal with these kind of bad examples. And in that case, I can think of the bound, right? So I'm wondering, have you like think of any like very bad examples where your algorithm might not work well?
Yes, we have used our algorithm to, because for example, portfolio selection, and its convergence rate its convergence result is very bad. So I'm not sure this is if the portfolio selection problem is our worst case or not. I'm not. I haven't thought of this situation before, so I think I should take some time to consider the worst case situation.
Okay, and I have also another question is that here the optimization problem you are considering is that unconstrained optimization or constraint optimization problem?
Oh, it's constraint optimization problem.
It's constraint. Okay. So do you assume that the number of constraints is finite or can be possibly infinite? I mean, do you assume that you have only a finite number of constraints, or it is possible that you can have infinitely many constraints?
I think it is the latter, because the problem formulation we consider is that capital C is only a non-empty closed convex set. So if we, so this is arbitrarily any subset in the entire space, like for example, the Euclidean space.
All right. Thank you.
Does that any answer your question?
Actually, not really, because for optimization problem, I might deal with is that you might specify a convex domain, right? Which is like the L here in your notation, and we also might specify some inequality constraints. And there are situations where there may be an infinitely many number of inequality constraints we encounter. In that case, we are interested in how to solve it. So, but here it seems that you assume that there is a convex domain L, and I do not see like other specific inequality constraint. So I guess it is quite different from the problem I'm thinking. But anyway, thank you.
Yes, you are welcome. So does anyone have any question? If not, I will stop here.
Okay, thank you, Junkai.
Okay, thank you.
I think we're all good.
Yeah, thank you.
We'll see each other in the next merge. I think it's mine. Yeah, have a good evening. Thank you very much, everybody.
Okay,
Goodbye.
thank you. Goodbye.